Okay, welcome to your first official lesson of our second unit on transformations. So we're looking at translations first. Now you'll notice that these first few lessons are going to seem pretty familiar because we've already actually looked at these concepts in our trig unit. So you might be able to breeze through them really quickly. Feel free to put the videos on a faster speed so you don't have to listen to me talk for so long, or just click through the videos and attempt all these examples on your own. I won't be offended. I won't know that you're doing it, but move through these videos at your own pace. I definitely anticipate, especially these first 4 lessons, will seem kind of old hand already, or it'll be good to talk, and it's always good to practice because we're going to be working with those different parent functions that we saw in lesson 0. So with that being said, we'll get started. So the big idea is that when we draw a graph, a translation is when we are sliding our shape around. So we haven't changed the shape at all. We're just moving where it is on our Cartesian plane. So that's our phase shift and our vertical shift that we're going to be talking about. So again, D is that vertical translation and C is our horizontal translation. Looking at our first graph, just bear with me. I have a typo in my notes that it should be x squared. So we are given the parent function here. So what I'm going to do is I'm going to use some different colors here to actually help me explain what's going on. Sorry, my voice is a little cracky today. I'm not quite sure why. So we've got y equals x minus 4 squared. So looking at our general equation, we know that our c value is going to be 4. And from our previous lessons, we know that when c is positive, that means that we are moving to the right. I always find, especially when working with our quadratic equations, that working with my vertex is the easiest. You may have found that last year in grade 11. So I'm going to move from 0, 0, positive 4. Otherwise, my shape should be exactly the same. So I'm going up 1 over 1, just like my parent function. And then 2 and should be 4. So you'll notice that they actually do still share a value. Again, getting that shape is super important. So I'm going to take a little bit. Okay, and so again, I would have that shape over here as well. A little bit even less bead than it. That's a little bit better. Okay, when I do this one here, my second one, I'm going to be looking at when c is -1, so that means I'm going to be moving to the left. So again, notice that my c values are opposite signs to what's in my equation, and that's perfectly okay. We just need to constantly remember that because of this negative in the general form, the fact that we're subtracting here, we have to change our c value. Move it left 1. And again, we can put in some points to help us sketch it out. And I always find it easier to draw that right side. I think it's because I'm left-handed. So if you're right-handed, maybe the left side's easier to draw. Okay, so I hope that makes sense. Left and right, that C shift. Okay, now we're going to see it noted a little bit differently here, but the idea is still the same, that we're looking for D. So we would want to just move it over onto the other side. And how we do that is we do the opposite operation. So we're going to subtract 1 from both sides. So that leaves me with y equals the absolute value of x minus 1. And now I know that my D value is going to be minus 1, or I'm moving my graph down 1. So I'm given the original parent function, my absolute value of x. So I'm going to shift that down 1, and my points will all be so. So it should look exactly the same shape. So all these lines should be running parallel to each other. That right side is just so much easier. Okay. So my next one, I'm going to do -3. So again, I need to move it over. So I'm going to rearrange to be y equals absolute value of x plus 3, which means that I'm going to move my graph up 3. So instead of having that sort of peak at 0, or that minimum at 0, I'm going to have it at 3, up 3 from where it originally was. And then from there, I'm still going to get those same values, that same shape, that same V shape. It's going to continue. Finally, if we're looking at this last one, y equals the absolute value of x plus 2 minus 1. Well, in this case, we have both c, which is -2, and d, which is -1. So we're shifting in both directions, horizontally and vertically. So it doesn't matter the order that you do them, as long as you do them both before you start putting your points down. So I'm going to go left 2 for that -2, and down 1, -1. I'm going to put it here. And now is when I'm going to start having some values that cross. And that's okay. That's what's going to happen if I've had both shifts, just based on the shape of my graph. But still, you can see that this line is parallel to the right side of the original parent function. And so again, we haven't changed the actual shape of it. Example 3. Okay, so again, we're looking at all these different parent functions, So we've got our parent function, in this case, is our square root. So when we're dealing with our square root, this is a d value of +2, so we're going up 2. So in terms of sketching it, I'm going to move my definitive point, or what we can call a critical point, something that kind of defines my graph. Then I'm going to include the same shape, and that's going to be my shifted up 2. For shifted within or underneath that square root, that means that it's my c value. I need to switch the signs, +3. So I'm going to move it over 1, 2, 3. But again, trying to keep true to that shape. Example 4. Now we're not given the parent function here, so we need to go back to our definition of those reciprocals. So we've got, the key thing is that at 1 and a 1 is still our defining point. Our asymptotes are at x equals 0 and y equals 0. And at -1 and -1 again, we're going to have one of those critical points that we can kind of rely on to know where it is. You want to make sure that that line never starts to look like it's going back away from your asymptote. That's why I read it up there. Okay, so that's my parent function. Once I've got my parent function, then I can looking at my translation. So +2 means that instead of x equals 0 as an asymptote, I'm going to be at x equals 2 is going to be my asymptote. Remember, always label your asymptotes. Otherwise, everything's the same. So my critical point is now going to be at 1 and 3. And my other critical point will be at -1 and +1 now, because that's also shifted up too. Okay. When we have our value actually in the denominator, that's when we're dealing with a C value. So it's within the function, inside our parent function. That's when where our C value shows up. We can still find our parent function, and then it's just a number on the outside. That's a D value. So here it's +3, because if I erase that circle, we can see it's subtract. So again, I'm shifting 3 to the right. So now I've got a vertical asymptote here. So Y, sorry, I mislabeled these to begin with. That doesn't help you. Y equals 0, X equals 0. So for the blue one, this is going Y equals 2. Sorry, that was my mistake. So we're saying X equals 3 here. So now we've moved over 1. My horizontal asymptote is still running along here because I don't have any vertical shift. D in the case of this second function is 0. No vertical shift or translation. So I'm going to be at 1 over for my asymptote and still at 1 for my Y value. Again, make sure it's getting close to your asymptote, but not actually crossing it. Again, that critical point, you can think of it as sliding it over 3, so from -1 to +2, or you can always look at it relative to the asymptote. And that's usually where I go. I go over 1 and down 1, over 1 and up 1. But again, you can always look at shifting those points individually. So for this second one, how we can do that is through what we call a mapping notation. So my original function was 1 and 1. That was a critical point. Well, after my translation, it becomes 1 plus 3 and 1. So now that becomes 4. Well, oh look, that's exactly where I put that point. I've also got -1 and -1 in my parent function. That's right here. Okay, and so I would go -1 plus 3, and my no shift in my D value because D is 0. Having done that, well, that's -1 plus 3 is +2, and that's exactly where I'm going to put that point and sketch in my curve from here. So if the mapping notation makes sense, that you would pick some points and apply these, I'll continue to show you how to do that. Actually, I'll go back and show you how to do that for this example as well. So using the same critical points of 1 and 1 and -1 and -1. They're just nice to work with, very simple points. Okay, well, D is 2 here, which means I'm affecting my Y value. So X value doesn't change, there's nothing impacting X in my function, but I'm going to take my original Y value and I'm going to add D. Same thing here, -1, -1 plus 2. So we get 1 and 3 as my 1 point, and that you see here, -1 and +1 here, and that's exactly what we plotted there. So again, that mapping notation can be really, really handy depending on your preference. So what this is doing is basically it's summarizing what we just talked about there. So when C is positive, it's translated to the right. When C is negative, the graph is translated to the left. And using mapping notation, that's exactly what we're seeing here. With C, we add it to our X value, and with D, we add it to our Y value. And so again, that's what we were doing up here. for example 5, then, if we know what our parent function is and we know the changes that are being made, then I can actually write the new equation. So my new equation, x is going to be 1 over, okay, so this is C, 3 units left. So that means -3. 2 units up, so that's D equals +2. So when I go to fill this in, I know +2 is just getting tacked on at the end. That -3 gets added in here. But remember that we should be subtracting C. So it's like subtracting a negative. So you might want to note this at least at the beginning until you get the hang of it. But eventually you may just jump to the point where you're like, oh, it's +3 if it's subtracting 3 up here. That would be my answer. So you probably want to practice this a little bit before we move any further. So pause the video. You're given a weird function. You can definitely use that mapping notation here. So choosing some critical points, some well-defined points to use, and then use the mapping strategy or just kind of counting, whatever you want to kind of try out to do this example. Okay, so if you attempted them, you should have 3 new drawings in addition to the original parent function that we were given. So this would be called a piecewise function, just FYI. Because it does a whole bunch of different things. You're not typically going to be asked to write an equation for them, but you will be expected to work within their graphs and values. So just to give you an idea of how I tackled this, I used the mapping notation just because it makes it a little bit easier, and it also let me keep track of individual transformations and put them together quite quickly. So that's how I did it. This is the general way I would have done it, and then individual examples using those special points that were easily defined on that original parent function. So when we look at example 7, describe how the graph of y 1 over x squared could have been translated to create each of the following, or each function below. What are the equations of the asymptotes of each image in the graph? So just a quick note, before we get going anywhere, I would want a picture of this original parent function. So we know that just x squared looks something like that with a vertex at 0, 0. So 1 divided by that, you would have learned last year, is going to have an asymptote at 0, because we're not allowed to divide by 0. So x equals 0, an asymptote. And because these values are positive on both sides, as opposed to our regular 1 over x reciprocal graph that looks like this, our 1 over x squared parent function is going to look like, not quite that, but yes. All sorts of issues. Still not okay. It's going to look like this. Of course, I don't have an x-axis to work with. Okay, on that side, and it would look the same on this side. It would be symmetrical, just like my parent function, that x squared function. And these points where it hits would be, again, those critical -1 and 1, and 1 and 1. And they don't change, because 1 divided by 1 is still 1, even when it's squared. Okay, so now that we have an idea of my parent function, now we can talk about everything else. So if you can't picture your parent function, make a table of values, generate the graph somehow. If you need to refer back to that initial page to start with, you're more than welcome to do so. So when we look at these, again, I don't like having my d value there. I like it on the other side. So I would rewrite this as y equals 1 over x squared plus 3. So now I can say with absolute certainty, now that I've moved that around, that the value for d is 3, positive 3, which means that it's moving up 3 from the parent function. Because of this, oh, and I should probably note that I do have a horizontal asymptote here at y equals 0. Just like with my mapping notation, my parent function would have been xy, and we could denote our translation x y plus 3. Well, that even applies to our asymptotes. So now, instead of my asymptote being at y equals 0, my asymptote would be at y equals 3. My vertical asymptote, because we didn't shift horizontally, is going to stay the same. Just like before. Now, when we get to this last example here, again, if you want to refer back to the parent function, we've got it higher up on the page. But what I want to note is that we've got, sorry, I'm finding that pen too fine. We need to move this 4 over, and then we deal with what's inside. So we've got y equals 1 over x plus 3 squared minus 4. Here I'm seeing both a c value and a d value. So c is going to be negative 3. Remember, always going opposite sign. D is negative 4. So that means that my translations are going to be left 3 and down 4. What does that mean for my asymptotes? Well, going back to that mapping notation, because I really like how it cleans everything up and makes it very clear about all our coordinates and really explains the relationship. So instead of x and y, we're going to have x minus 3 and y minus 4. How does that affect my asymptotes? Well, now it's going to impact both my asymptotes. I've shifted horizontally, so that vertical asymptote is now going to be at x equals negative 3 instead of 0. And that horizontal asymptote is going to be at y equals negative 4. And so again, we see this because we've impacted both coordinates of my coordinate system by having both a c and a d value. So I'll be posting some homework to go with this, but I hope that that's clear. Again, I think the biggest adjustment here, because we're seeming pretty confident in our last unit on the idea of transformations with trig functions, that we're going to start applying them to different shapes of graphs. So whether they're piecewise functions, reciprocal graphs like we're seeing here, or we've got our different shapes, again, back up here, absolute values, square roots, quadratics, they're all going to come into play now. So I hope that that helps. And again, like always, please do email if you have any questions whatsoever. I really do like to help. It's my job to help, and it's only going to benefit you to ask.